In this problem, we want to find a power series representation for the function and determine the radius of convergence. Here our function is f of x equals x divided by 6 plus x squared. Now again, everything in this section depends on the geometric series. We know that the sum from n equals 0 to infinity of x to the n is equal to the function 1 divided by 1 minus x for x values with an absolute value less than 1. So we need to relate our function f of x to the function 1 divided by 1 minus x. You will notice in the function 1 divided by 1 minus x, the denominator is not squared. So after thinking for a little bit, I'm going to make up a new function. I'm going to call it g of x, and I'm going to let it be 1 divided by 6 plus x. Okay, now why would I want to do this? If I take the derivative of g of x, I would get negative 1 divided by 6 plus x, quantity squared, which more closely resembles our function f of x. So f of x would then just be negative x times g prime of x. So I'm looking at this problem in two steps. First, I'm going to find a power series representation for 1 divided by 6 plus x. Second, I'm going to take the derivative to find a power series representation for negative 1 divided by 6 plus x squared. And third, I'm going to multiply that power series by negative x to get a power series representation for our function f of x. So for step 1, I'm looking at 1 divided by 6 plus x, and I'm rewriting it so that the denominator has the form 1 minus an expression. So I'm going to multiply the top and bottom of this fraction by 1/6. That gives us 1/6 divided by 1 plus x divided by 6. I can pull this 1/6 out front, and then in the denominator I will write 1 minus negative x over 6. The point of doing this is that I always want to see a fraction 1 divided by 1 minus something, and that thing is the common ratio. So this is 1/6 times the sum from n equals 0 to infinity of negative x divided by 6 to the n power. This is where we used our geometric series. Simplifying, we have 1/6 times the sum from n equals 0 to infinity of negative 1 to the n divided by 6 to the n times x to the n. And then multiplying that 1/6 that's out front into the term, we have negative 1 to the n divided by 6 to the n plus 1 times x to the n. Okay. In step 2, we want to take the derivative of this function. So we're going to find an expression for negative 1 divided by 6 plus x squared, which we know is the derivative with respect to x of this power series, n equals 0 to infinity, negative 1 to the n times 6 to the n plus 1, x to the n. When we take the derivative, we have a theorem that tells us that we can put the derivative inside this sigma notation. So I can take the derivative of each term separately and then add them together afterwards. Now, we know that this is true for finite sums. The interesting thing in this section is that this is also true for infinite sums as long as we have a power series involved. Now, I want to point out that the first term here, when n equals 0, we have the derivative of Negative 1 to the 0 is 1. 6 to the 0 plus 1 is 6. And x to the 0 is 1. So we have just the derivative of 1/6. And then I'm writing down the rest. Now the reason I wrote the 1/6 down separately is that we know the derivative of a constant is 0. So this first term is 0. In the rest of the terms, the variable x has a positive exponent, so we take the derivative just by using the power rule. We have the sum from n equals 1 to infinity, negative 1 to the n divided by 6 to the n plus 1 is a constant, and by the power rule, the derivative of x to the n power is n times x to the power n minus 1. I need a little more space for step 3. So for step 3, our function f of x is negative x times negative 1 divided by 6 plus x squared. Or in other words, negative x times the power series from n equals 1 to infinity, negative 1 to the n, divided by 6 to the power n plus 1, times n times x to the n minus 1. Now I'm just going to take this negative x and multiply it into the terms. We have the sum from n equals 1 to infinity of negative 1 to the power n plus 1, multiplying negative 1 to the n times negative 1, times n times x to the n power, multiplying x times x to the n minus 1, all divided by 6 to the n plus 1. And this is our final power series representation for the function f of x. Now we need to talk about the radius of convergence. I'm realizing that I erased step 1, so let's recap what we did.
We have 1 over 6 plus x. We multiply top and bottom by 1 over 6. And then we wrote this as 1 minus negative x over 6. And we said that this is the series n equals 0 to infinity. We have 1/6 times this series, negative x over 6 to the n power.
Now the interesting step for the radius of convergence is when we write this function as a power series, this is true if the absolute value of that common ratio, negative x divided by 6, is less than 1. In other words, the absolute value of x divided by 6 is less than 1, so the absolute value of x is less than 6. So the radius of convergence is 6. Now, there was the step when we took the derivative of our power series, part of the theorem that tells us it's okay to take the derivative of each term separately tells us that the radius of convergence of the new power series is the same. So the radius of convergence of our final answer is also 6.